So there were some main things with our heating curves yesterday, where we're talking about kinetic and potential energy, we're talking about temperature, and the main thing is that you have to remember whatever temperature does, that's what kinetic's doing. There's that direct relationship. And that's going to hold true as we start into these cooling curves as well. So cooling curves, like I had said, are basically the exact opposite, or the reverse, I guess, of what's going on in a heating curve. A cooling curve does what it sounds. It's showing a system that is cooling off. So this is a graph that's going to show the relationship between the molecular kinetic energy and potential energies within a system as heat is leaving, right? So leaving makes this exothermic. And so as that thermal energy, also known as heat, leaves, we know that temperature decreases. Obviously that makes sense. If something's getting colder, the temperature's going down, right? Not too hard, there's nothing to remember or try to memorize there. Just think about it logically. And so we know that whatever temperature does, that's exactly what kinetic energy is doing. So if temperature is going down, kinetic is going down. They do the exact same thing. There's a direct relationship there. All right, so when the temperature is not changing, but thermal energy is being taken out, that's when we're getting a change in our potential energy. So just like yesterday with the heating curves, as we were pumping heat into the system, if the temperature is not increasing, it has to be going somewhere. And what it's doing is it's actually going into the potential energy and causing that attraction to be changed between those molecules. So it's changing that positioning, and that's a potential energy. Remember? What's kinetic energy? What's the main way to remember kinetic energy? It's the energy of what? Motion, movement, right? So potential energy is the energy of positioning, like with how the molecules are arranged, or that stored up energy. Okay. All right, so if whatever temperature is doing, that's what kinetic does. And if you're putting thermal energy into a system or taking thermal energy out, but the temperature is not changing, that's when you're gonna, get a change in that potential energy. All right, so this looks a lot like your heating curve that we looked at. Excuse me. So we have temperature in degrees Celsius, and then down here we have time in minutes. Remember, most of the time it's going to show time down here. We know this is really as thermal energy is being added or removed from the system. So in this case, thermal energy is being taken out, so it's cooling things down, but they show that in time. There was one of the graphs from yesterday that showed thermal energy, and I like that better because it helps you visualize kind of like, okay, heat's going in or heat's coming out, instead of just looking at time. But we know as time goes by, thermal energy is being taken out or thermal energy is being put in during these curves. So we have our temperature here on the side, and here you see segment AB, BC, CD, DE, and EF. Okay? So this is showing as you start at a gas, because you're at the highest temperature there, right? If this is dealing with water, you're over 100 degrees Celsius, so that means that it has all boiled away and you have nothing but the steam version, okay? And so again, this is an exothermic process because heat is exiting this system. Okay? This is the process that releases thermal energy into the surroundings. So the air around this fire is getting warm because it's leaving that chemical combustion or burning reaction. So exothermic pairs up with the cooling curve. Think of heat exiting, well then it's going to make something cooler, and you have a cooling curve to show that. Again, logical, common sense. It's not something that you have to really worry about, trying to memorize it. Just think about it. You know, if things cool off, it's because the temperature's gone down, and it's because heat has left the system. All right, so heat exits. Exothermic exits. All right. So here's a cooling curve. This is like on the bottom right, you have the graph, right? So those segments A, B, B, C, C, D. So again, it's gonna explain, just like it did yesterday, what's going on as you go down that curve. All right, so from that segment AB, that's kind of like a downward segment like this. It's the cooling of a gas where you have one phase present and kinetic energy is going down. We know kinetic energy is going down because the temperature is going down. When you go to BC, it's kind of like that horizontal plateau area. This is the condensation of the gas going to a liquid. There are two phases that are present. Two phases because you're dealing with a gas that is changing into a liquid. So you have some gas and you have some liquid still. Two phases, that's that plateau area, that is that flat line, that's where potential energy is changing, but kinetic is staying the same, and we know that because the temperature is staying the same. So kinetic energy is constant because the temperature is constant. Then as we start to go down again, so this is the segment CD where it's kind of like the downhill. It's the cooling of a liquid. So it's all one phase, it's all liquid. All the gas has now been condensed into water, and we have kinetic energy going down, and we know that because we see that the temperature is going down. So I think, just like I said yesterday in the notes, it's easier to kind of figure out what kinetic energy is doing because all you have to do is look at the temperature, okay? If the temperature is changing, kinetic is changing, right? Specifically, if it's going down, that means kinetic's going down. Or in a heating curve, if the temperature's going up, then that means that the kinetic is going up as well. All you have to do for potential is find those flat line, those plateau areas, right? Those are the 3 P's in your vocab: the plateau, phase change, and potential energy. All those things go together, so all you have to do is look for that plateau area. Okay, DE. Now we're back to another flat line plateau. This is called the solidification, or more specific, the freezing of a liquid. So you're going from a liquid to a solid. Okay, saw this yesterday in our horse trailer. We had washed it in our shop, backed it in our barn, and it was dripping, and the barn was cold, and we have like rubber mats for the floor. And I was walking by the horse trailer, and there's like, I thought it was a puddle of water. It was a puddle of ice. Not really a puddle at that point, but it like turned like into black ice. Like it looked like it was just water, but I took a step on it, and like I was kind of like walking slow, thank goodness, and like my foot hit it, and I was like, whoa, like that is already ice. So our barn was pretty cold, but the trailer had still been warm from when it had been washed in the shop where it was warm, and so that liquid was dripping off and made that nice sheet of ice kind of looking like this. So it was going through that, and it made me think of today, talking about this, going through that freezing process, going from the liquid to the solid. All right, because we are at, we have two phases, it's at the plateau, we know that that's where our potential energy is changing. So when you see on the graph, that segment right there where it's plateaued or flat, you know potential energy is changing. The attraction of the molecules is coming closer and closer together. They can't overcome the attraction. They're coming back together to make that solid. And then finally, we get to the very bottom right-hand side of the graph, right? That section E to F. And this is the cooling of a solid. So the solid is getting colder and colder and colder, okay? You have one phase present. Kinetic energy is going down because the temperature is going down. Right, so there's a lot of general characteristics between these heating curves and cooling curves. And once you kind of get the hang of, and we're going to do a lot of practice with this, but once you get the hang of it, it's not really as complex as it seems, right? Kinetic energy, you're talking motion. So the molecules speed up as they get warmer. As they cool down, they get closer together, okay? That's kind of the key. Maybe. Okay. So we had looked at sublimation and deposition yesterday as two of our big phase changes, and we're just going to talk about them again just because they are a little bit different than the others. This is where you have the two phase changes that skip the liquid state. So it's not a complete heating or cooling curve, right? You just go from the gas to the solid or the solid straight to the gas. So again, sublimation is solid straight to the gas. And they showed this with dry ice. They also showed this with the purple iodine solid yesterday. And then they had the, it went from the solid and then you saw the purple gas form, right? There was no melting going into the liquid. That was all skipped. Deposition is a gas straight to the solid. And then they showed the reverse of this when they put the ice cubes on the watch glass and it cooled that gas, and that gas was able to go straight back to the solid, and then it kind of stuck to the bottom of that watch glass. The example that I gave yesterday was frost, right? It's that simple process. If there's moisture in the air and it's kind of coating everything, if the object that it's going to land on is colder than the air around it, it will make it go straight to the solid. You don't get the dew. It's basically like frozen dew. You skip the dew and it just goes straight to the ice version or that frost, right? And so that happens a lot right now this time of year. So you can see it when we have grass and not snow. You can see it in the snow. You can see it on bushes if your vehicles are parked outside. And so think about, again, from 8th grade science, that deposition process with weathering, erosion, and deposition. Deposition's the dropping. Same thing here. It's the dropping of the water vapor in the air onto whatever object, it's coating. Okay. So we have that deposition. Okay, so let's take a look. I'm kind of curious. So they're calling this section A, B, C, D, and E. So let me ask you, and here we have temperature, here we have time, knowing that this is where we're increasing. So temperature is going up here. So this is going to be showing us a heating curve. It is also going to be an endothermic process because it's taking that heat into the system. Everybody agree with all that? All pretty logical? So if we're talking an endothermic process here, as I go from A to E, it's warming up. So give me one of the sections where the kinetic energy is increasing. Which one of these sections, and there's more than one, give me a section where the kinetic energy is increasing. And think about what kinetic energy matches. What do you think?
C.
Okay, I like it. Why did you pick C? How did you know?
Because as kinetic energy increases, so does the temperature, and on C the temperature increases.
Very nice. Are there any other places where you see temperature increasing? What do you see?
E.
Okay. Going up there. And what else? What do you think, Breeze?
A.
Temperature's going up there. So temperature's going up in A, C, and E. So because temperature's going up, automatically we know kinetic energy is going up. Great explanation, Kate. All right, where are we going to see two phases happening at the same time? Is it going to be A, B, C, D, or E? Where are we going to see two phases taking place? Think of the 3 P's. Oh, I can wait you out. Heard somebody whisper B. I don't know who it was. You're right. B is a plateau, right? Plateau means phase change, plateau, and potential energy changing. So anywhere where you see that flat horizontal. So phase change means two things are present. If this is if this is a solid and this is a liquid, this is kind of like the bridge to get you from the solid to the liquid. So you're gonna have both phases present there for a little bit, right? Until it's all melted to the liquid. So where else are you gonna see the same thing happening where you have two phases and you have potential energy changing as well? What's the one that kind of matches with B? Right? You guys just sleepy, or are you not with me? I'm sleepy too, like, I'll admit it. It's making sense? Okay. All right. Let me skip that. All right, let's go, we need to do some practice. Let's go to Kahoot.